Good day, everybody. And once again, we're back together. So we're looking at question 4 from the November 2024 exam. So please, if you haven't subscribed, just make sure you're part of this family. Right, so let's dive right into it. So this has been brought to you courtesy of Naledi, who has requested us to go through this paper. She wrote to us and asked us to have a look at this. So thank you, Naledi. Shout out to you. It's really nice to have you interact with us via email and over social media platforms as well. So let's get into it. They say, explain why this can be classified as a closed system. So they said the image shows a saturated aqueous solution of silver phosphate at 25 degrees. So it can be classified as a closed system in this case because none of the reactants or products can escape, right? So we can say that mass of reactants and products remains constant. Okay, or you can say the reactants or products cannot leave the system or cannot escape or does not escape in this case. So that is also quite plausible. All right, let's go to the next one. They say the equation below represents the equilibrium reaction occurring in the solution. Okay, right, now they say to you, give the name of Ag3PO4. I think I just gave you the name right now. We said this is going to be silver phosphate. So that's silver phosphate. Okay, if you want to, in fact, you know what, let's just leave it as is. So they say correct, circle the correct answer within the brackets. The forward reaction is A. So this is a dissociation reaction, okay? What we are simply doing there is that we're taking a whole compound in that case, and we are breaking it down into different ions, okay? So this would be a dissociation reaction. Okay, so then they say to us the value of Kc indicates that the yield is extremely. Now notice the Kc value is very small, so it's telling us that the yield is very low. Okay, right, and they say to us, write down the expression for the equilibrium constant for this reaction, and what it would look like is Kc, it's the molar concentration of our products. So we've got Ag plus cubed multiplied by PO4 3 minus, okay, that's to the power 1, but note our reactants are in solid form, so in that case we do not include them in our expression. So that's what our expression will look like. Right, now they say to us, show that the concentration of phosphate ions is ions in the saturated solution at 25 degrees is given by that. Now, we already have the Kc expression, isn't it? And what do we notice? That whatever happens in this case, let's just say for argument's sake, that we produce an X amount of phosphate ions. How much will we produce of the silver ions? It will be 3X, right? So that means if we take our equilibrium or our Kc expression, means we'll have 3X, remember, that's cubed, multiplied by X. In this case, that will be equal to the Kc value, and our Kc value was given as 8.9 times 10 to the power negative 17, right? So 8.9 times 10 to the power minus 17. Okay, so that's 3x cubed, which will give us 27. X cubed times x, that will be x to the power 4. And this is equal to 8.9 times 10 to the power negative 17. Okay, let's divide both sides by 27. And we are going to take the quad root of it. So let's take that. That's 8.9 exponent minus 17 divided by 27. Okay, and I get that answer. And now we are going to take the we need to do this properly. The fourth root of the answer. Okay, and there we go. Right, I'm going to write it in. So x in this case gives us 4.26 times 10 to the power negative 5, right? That's moles per cubic decimeters. But what did we name x? That was the amount of phosphate ions. So the concentration of our phosphate ions will be equal to 4.26 times 10 to the power negative 5 moles per cubic decimeters. Right, I hope that is clear, ladies and gents. And now they say to us, hence calculate the total number of free ions of the solute present in 0.2 cubic decimeters of a saturated solution of silver phosphate at 25 degrees. Now remember, what do we have? We've got phosphate ions, but we also have silver ions. Now we know that we've got 3 times as many phosphate ions, so we can say the number of moles, now this is only for phosphate ions, PO4 3 minus, that's concentration times volume. Right, now the concentration of these, we just got it from the above. That's 4.26 4.26 times 10 to the power negative 5. Okay, multiplied by the volume, which is 0.2. Okay. Right, so let's calculate that quickly. Okay, that's going to be times 0.2. And that gives me 1.2. In fact, let's just be absolutely certain. Sometimes when we get an answer using this calculator, that's minus 5 multiplied by 0.2. Okay, yeah, we are definitely sure. So I'm going to give that in scientific form. That's 8.52 times 10 to the power negative 6. That's moles. Now remember, this is for phosphate ions, right? But when we want the number of molecules, now remember, we still need to multiply this with Avogadro's number, right? So I can say, well, remember, on Avogadro's number, I would take the number of moles, or you can say that's number of particles divided by the, divided by Avogadro's constant, right? So we've got the number of moles. We know Avogadro's constant, right? That's 6.02. Okay, so if we want the number of particles, that would be 6.02 times 10 to the power of 23, and that will give us the number of particles. But remember, that's for phosphate ions only. we still need to find out the number of particles for silver ions. And we remember from our reaction, where's our reaction? There it is, right? We've just calculated these particles. We need to find out the other particles as well. Okay, so all that we need to do, ladies and gents, we've just found out the number of moles there. It will be 3 times the number of moles over there. Okay, so that means let's do this. Okay, let's calculate. Multiplied by 6.02 times 10 to the power 23, and that will give us 5.13 times 10 to the power of 18, right? That's particles. But remember, those were just for phosphate ions, so which means if we wanted to find out the number of particles for what was the other one? I think silver ions, that's 3 times the amount. So number of particles for silver, that's going to be 3 times this amount, 5.13 times 10 to the power 18. Okay, but remember in total, so the total number, it would be the number of particles for phosphate plus the number of particles for silver. Okay, so we might as well have just multiplied this by 4 because it's 3 plus the other one. So in that case, we will just have, let's take that. What did we just do? So that's 4 times 5.13 exponent 18. Okay, and we get a number 2.05 times 10 to the power 19 particles, right? So that's what we have in total. Right, so those are all the free particles that we wouldn't been able to obtain. Right, let's go on to the next question. Now they say to us, how will the concentration of silver ions in the saturated solution be affected in each of the following instances? Right, they say write down only increase, decrease, or remain the same. Now they say if the solution is heated. Now notice this is an endothermic reaction, so if we increase the temperature, we're going to favor the forward reaction, right? So in that case, it means if we heat the solution, we're going to end up with an increased number of silver ions. So we will say increase there. Okay, now they say to us a few crystals of sodium phosphate. So remember, this is now, we are going to use the common ion effect. It means you are increasing the concentration of phosphate ions. That will cause the reaction, the reverse reaction to be favored. Okay, and that would mean that the silver ions would decrease. Okay, and they say a few crystals of silver phosphate are added. Now, ladies and gents, I want you to note that silver phosphate is a solid. So in that case, even if you add more of it, nothing will happen to the concentration. So in that case, it remains the same. All right, and finally, they say explain the answer to 4.7.1 by applying Le Chatelier's principle. And please, ladies and gents, refrain from making this long. You're just going to go straight to the point. Right, so for 4.7.1, we say an increase in temperature Okay, an increase in temperature favors the forward reaction, favors, in fact, first the endothermic reaction, okay, all right, the forward reaction is endothermic, therefore it is favored, right? Right, and so that will increase the amount of silver ions, right? So please remember, an increase in temperature will always favor the endothermic reaction so that it can decrease the amount of heat that has been added, okay? Right, and then next, but they say to us, give a reason for the answer to question 4.7.3. Which one is that? All right, so please remember, in this case, so they are essentially just asking us, why is it that it would remain constant in that case? Yeah, that's the one. Okay, right, so essentially we can say that no more Ag3PO4 can dissolve because they also told us that it is a saturated solution, right? So in that case, please just note also it being a solid would not necessarily affect the rate, or rather the rate of the reaction, and thus would not shift equilibrium as well. Ladies and gents, that brings us to the end of question number 4. So we'll come back with question 5. Please look out for the rest of this question paper, and I hope that this is really helpful. For now, I'll leave it there. Till the next one, sharp, sharp.